Okay, so our speaker today is Rishav Roshan. Rishav is currently doing is a research fellow at Southampton in the United Kingdom. He got his PhD at the Indian Institute of Guwahati in 2021, and he also did a postdoc in South Korea at Kungphook National University. Okay, and today he's going to talk about a topic which is very, very of the moment and very interesting to me, and I hope many of the others in the audience, which is on using gravitational waves to see the early universe. Okay, please start, Rishav.
All right. So first of all, I would like to thank Peter for such a warm welcome and giving me this chance to present my work. So as he said, I'll be talking on how we can use gravitational waves to see the early universe. And this talk is mostly based on a recent review that I wrote with Professor Graham White and a couple of my other works. And following these are the list of my collaborators with whom I have worked on this topic. Just wait a minute. So now I'm not able to change the slides. Yeah. So this is the plan of my talk. So I'll briefly introduce some high-scale physics or early universe physics, where I'll be talking about dark matter, antimatter symmetry of the universe, scale of quantum gravity, primordial black holes. Following which I'll be discussing the gravitational wave, a little bit of theory about gravitational wave, what are the various sources that we can think of in early universe that can actually generate gravitational wave. Then I'll talk a little bit about different detectors, and then I'll talk about the recent discoveries of gravitational wave signals. Now, after that, I'll be discussing in a bit of a detail about different sources that actually includes domain wall and how it can generate gravitational wave and what are its application. And then I'll be talking about the gravitational wave generation from cosmic string and its application. And finally, I would discuss the scalar induced gravitational waves from PBH. And again, what are its and again I'll talk about its application. And finally, I'll be summarizing and concluding. So to start with, we in last couple of decades, we have a good understanding of how our universe evolved. But then there still exists some cosmological puzzles like inflation, origin of dark matter. We don't know why there exists a plethora of matter over antimatter. We don't know what is the scale of quantum gravity. We don't know much about primordial black holes. Now, all these things actually motivates us to look for a physics which is beyond the standard model. As I said, like all these phenomenologies happened in the early universe, and hence corresponds to high scale physics. Now, another important thing is that how to detect these, or how to probe, or how to test these puzzles. So actually, cosmological observations plays a powerful investigative tools in this direction, and gravitational wave is one of them. So let me give a brief introduction of these high-scale physics. So to start with, I would like to discuss dark matter. Now, we all know about the evidence of the dark matter, right? For example, we know about the galaxy rotation curve. So what does this suggest? This suggests that we have felt the gravitational pull of dark matter. Now, this suggests that dark matter is massive, but what we don't know is we still don't know about its particle nature. So in summary, what we know about dark matter, it's how much it is available in the universe. We definitely don't know that it is massive. And since it exists in the universe, we know that it is stable. It's not decaying. We know that it either interacts very weakly or it does not have any interaction with the standard model particle spectrum. What we don't know about the dark matter is, again, its particle nature, how it actually interacts, and how it was produced in the early universe. So as I said, like the only concrete thing that we know about this dark matter is that it has mass. But how massive it can be, we don't know. It can be very massive, it can be light. So if it is very massive, how can we probe? So this is the one question which is always there in our mind. Next thing is the plethora of matter over antimatter. So we know that like once the universe was created, particles and antiparticles were created in the same amount. But at some later stage, something happened and we were only left with the particles. So what happened to these antiparticles? We have no idea. So there was a asymmetry which was generated. So we quantify this asymmetry as a ratio of the difference between the number density of particle and antiparticle to the entropy density. And this ratio is of the order of 10 to the power of minus 11. And in order to explain this, we generally consider a physics which is at a high scale. And again, one can ask how to test these scales. Next, I would like to talk about the scale of quantum gravity. Now, as we all know that EFT has played a very vital role in particle physics. It has guided physicists looking for a new physics signature. But once we talk about quantum gravity, or it has certain limitations, because the situation actually becomes a bit difficult or a bit different when we include gravity and try to demand that EFT in question is valid at all energy in the suitable theory of quantum gravity. Now, with this in mind, string theorists developed the idea of swampland, which says that, or swampland refers to all the low energy EFTs which are not compatible with quantum gravity. And following this, they developed swampland conjectures. And these are some of the well-known conjectures. The first one is no global symmetry conjecture. Then we have weak gravity conjecture, distance conjecture. But let me tell you that I'm not a string theorist and I do not know this thing in very detail. So the next thing I would like to talk about is the no global symmetry conjecture, and it's a bit easier to understand. And this is the most well-known conjecture. So it says that like we do not have a symmetry which is a continuous or discrete symmetry which is exact in the theory of quantum gravity. So what does this mean? That if we have a symmetry at low scale, it will be definitely broken at high energies by quantum gravity. So the next question one can ask is that, is there any observational effects that can constrain the scale of quantum gravity? Next thing I would like to talk about is primordial black hole. We know that primordial black hole has a very good physics, very good phenomenology, because it can play a role of the dark matter if it is stable, depending on its mass. And if it is light enough, it is actually unstable and it can actually produce uh, particles which are stable and can play the role of dark matter. So the thing is that like the phenomenology wise, PBHs are quite rich, but again, there is no cosmological observation. So one can ask that, is it possible or are there any observational effect of such PBHs? So these were some high scale physics that I'll be covering in my talk, and how we can use this to understand the high energy physics or high scale physics, and how these sources can produce gravitational waves, and how we can relate actually gravitational waves with those cosmological puzzles, and how we can use gravitational waves to test actually those cosmological puzzles. So again, now let me talk a little bit about the gravitational waves. So what actually is gravitational wave? Now one can start with Einstein equation, which actually suggests that or shows that space-time determines how space-time determines the trajectory of all the objects, or in other words, how massive object actually curves the space-time. Now, if we consider a small perturbation, a very tiny perturbation around the metric tensor as shown in this equation, here eta mu nu is actually the flat space-time. It represents the flat space-time, and h mu nu is actually a very small deviation in the flat space-time. Now, once we substitute this back into the Einstein equation and use Lorentz case, what we find is that one can write, one can actually use it to calculate the how the gravitational wave propagates. So this can be expressed using this equation. And here on the right hand side, it's basically the source term that actually can generate the gravitational wave. Now, if we consider a far field regime, that means we are quite far away from the source where it was produced. One can approximate this amplitude of the gravitational wave in the following way, where this q is actually the quadrupole moment, and it basically depends on the second derivative of quadrupole moment. Now, one can ask that why not monopole or dipole moments? So the thing is that, like, when we do this multipole expansion, what we'll find is that the term related to monopole and dipole actually vanishes because of the conservation of mass and momentum. Now, another takeaway from this equation is that you see this term, the amplitude actually depends on the derivative. That means one cannot generate gravitational wave with a static object. So there should be a movement. Now, the power emitted from the gravitational wave signal can again be written in the following manner. So this was a little bit theory that I wanted to discuss before going into the detail of how gravitational waves are actually generated from different sources. Now, again, so what could be a possible source of gravitational waves in the early universe? So what we know is that gravitational waves propagate freely once they are generated, and they do not interact. And we know that they do not interact with anything. So that's why it actually carries a unique information about the process which actually have produced them. Now, what could be the possible sources in early universe? It can be generated at the time of inflation. It can be generated if the universe went through some phase transition, or if there exists some kind of topological defect in the early universe. It can also generate gravitational waves. And it can also be generated from primordial black holes if they existed in the early universe. Now, on top of generating the gravitational waves, these sources can also help us in understanding some of the cosmological puzzles that I was telling you about. That means this defects or this phase transition or these black holes can actually produce particles, which is responsible for the relic density of the dark matter relic density of the universe. It can produce unstable particles that can decay and generate the asymmetry which is present in the universe, or they can themselves produce primordial black holes. I mean, the topological defect can collapse and produce primordial black holes, and it can also be produced from phase transition. So a simple question that one can ask is that, can we use gravitational waves to test or probe these high scale physics? And it seems that yes, because they might have a common origin. Now, let me talk a little bit about the detection possibility of the gravitational waves. Now, we have several detectors, some Earth-based detectors like LIGO, Virgo, ET. Then we have the space wave. Then we can think about space wave based detectors like LISA, BBO, DESIGO, mu arrays. Then we also use pulsar timing arrays actually to detect gravitational wave signatures. So the thing is that all these detectors actually work in different frequency regime, and it actually covers a huge range of frequency. Now, depending on the source from which the gravitational wave is generated, the wave can have different frequencies, and hence one can use these detectors to actually detect those gravitational wave signatures. And note that these signatures, I mean, the amplitude is the signal of a gravitational wave signal is actually very difficult to detect. So physicists have worked quite hard to detect these signatures. So the next question one can definitely ask is that, why should we spend huge amount of money on these gravitational wave detectors? So the answer is, actually we have detected gravitational waves in past couple of years. The first discovery was done by LIGO Virgo in 2015 that suggested that the gravitational wave was actually originated from the merger of black holes. Then we also have the recent discoveries by PTA project that detected gravitational waves with a frequency of nanohertz. And this actually suggested something very important. this small frequencies can only be generated at early universe because of the, and it might be generated because of the merging of supermassive black hole binaries, or it can be originated from some, it might have some cosmological origin, or it might be a combination of both. So in this nanograph paper that discussed this result, it suggested that one can think of a different sources, like these gravitational wave might have been produced from the induced gravitational wave. Then one can think of a scalar induced gravitational wave. Then one can think of a different string possibility. Then it can also be generated from domain walls. So it suggests that the sources of the gravitational wave was from high energy physics, high scale physics. Now again in 2017, uh, due to the discovery of gravitational wave, it actually earned Nobel Prize. So now this was a little bit discussion, or I discussed a little bit about different sources of high scale physics, or different high scale physics scenarios. Then I talked about how or what gravitational waves are, how it can be generated in the early universe. So, as I said, I'll be mostly focusing on three sources that can actually generate gravitational waves in the early universe. And first of them is domain wall. So here I list some of the recent uh, works that has been done in this direction, and these are two very important. I mean, the works in the red are the first one that was discussed by Nanogram, as it suggested that domain wall can be the source of uh, these gravitational wave signals. And then there is this another work which is a very good review on gravitational wave from domain wall. So let me talk about uh, what domain wall actually is. Domain walls are actually two-dimensional topological defects, and they are formed once a discrete symmetry is spontaneously broken, for example, a Z2. Now, what happens is that once a discrete symmetry is spontaneously broken, we get a two degenerate vacuums, and this leads to a formation of two domains, which are separated by a wall, which we call it as a domain wall, as we can see in the figure in right. So we have two different domains, one with plus, one with minus, and the green line actually denotes the domain wall. Yeah, so once we solve the equation of motion, one can write the scalar analytical expression for the equation of motion. And it depends on two things. One is the quartic coupling that appears in the potential. And next thing is the vacuum expectation value at which the symmetry was broken. So yeah, and then the another important thing about the domain wall is its surface tension, which again depends on the self-quartic coupling and the vacuum expectation value of the scalar. But apart from this, another important information about domain wall that I want to give is that its energy density actually varies very slowly. It actually goes inversely, it's actually is inversely proportional to the scale factor of the universe. That means that it dilutes much slower than radiation and matter, as can be seen from the figure on right. So here I show the evolution of radiation with the scale factor in black dotted line. Then I show the evolution of matter with the scale factor in blue dotted line. Finally, in red solid line, I show how the energy density of domain wall evolves. And you see it, and one can see that the, there will exist a time when the energy budget of the universe will be dominated by the domain wall, as can be seen from this plot. This actually is a cosmological catastrophe because it's constrained, it might affect the fate of CMB. So this is a problem. Now, the obvious question one can ask is that how can we handle this problem? So there are possible solutions present in the literature. The first one can think of is that, like, if the domain walls are formed in the early universe before inflation, then they can be inflated away. The second solution can be the restoration of symmetry. That means that if the domain wall was formed at some temperature, because of the breaking of this symmetry, some symmetry, this symmetry can be restored at some other temperature, and hence one can resolve the problem of domain wall. But the most well-known solution of this domain wall issue is creating a metastable domain. So what do we mean by metastable domain? Because we saw in the last slide that once the symmetry is broken, the vacuums are degenerate, and that's why the domain walls are problematic for our universe. Now, if we make the domain wall metastable, that means if we introduce a bias term in the potential, this will destabilize the vacuum, and this will destabilize the domain wall. So what happens is that because of this bias, the domain wall now has a pressure force, basically pressure force. And then apart from the pressure force, the domain wall also has a tension force because of its surface tension. Now, once this pressure force or volume force actually becomes larger than the tension force, the domain wall, or basically the false vacuum, actually starts to shrink, as we can see again on the plot on the right. So because of the introduction of this bias term, the domain wall starts to, the false vacuum actually starts to shrink. Now let us see how it can actually generate gravitational wave. It can actually generate gravitational wave in a following manner. The thing is that during the early phase of domain wall, when the bias was created, its dynamic is changing. It's changing its shape. So that's why it wobbles, and then it releases energy in form of energy in form of the gravitational wave. So if we look at the spectra on the right, it's actually the left part from the peak. It's this 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 rise is because of the domain wall generation, gravitational wave generation from the wobbling of domain wall. Now, then at some point of time, the annihilation of the domain wall actually starts, and this corresponds to this red dotted line. And after which the domain wall keeps on annihilating until unless it disappears. So this peak in the spectrum actually corresponds to the time when the domain wall annihilation start. And frankly speaking, we do not have much idea of how actually the domain wall annihilate. So that's why this region, we do not have a very concrete evidence on the this region on the right. So as I said, the one can calculate the energy density of the domain wall, gravitational wave generated from the domain wall, and we can use it to calculate the gravitational wave amplitude. And the peak amplitude actually depends on two quantity, which are the surface, which is basically the surface tension and bias. That means that both of these things actually depends on the self-vortic coupling and the breaking scale of the Z or discrete symmetry. Similarly, the peak frequency also depends on the surface tension and V bias, and hence it also depends on the quartic coupling and the breaking scale. So this was a little bit idea about when and how the gravitational waves are actually generated from domain wall. Now we can think about its application. So we did a recent work uh, where we tried to see how the gravitational waves generated from a domain wall can actually help us in constraining the scale of quantum gravity. So the idea was fairly simple. We used the third and the most used or most well-known swampland conjecture, which says that the no global symmetry is exact. So what we did here was we considered a stable sector which had two two scalars, S1 and S2. S1 is considered to be odd under one Z2, one discrete symmetry, and we call it as Z2 domain 1. S2 is odd under a different Z2, and we call it as Z2DM. So this Z2DM is actually responsible for the stability of the dark matter because it remains unbroken. And Z2DW is actually responsible for the generation of domain wall because it is spontaneously broken. And once it is spontaneously broken, we will get a degenerate vacuum. Now, as I said, the quantum gravity will break any global symmetry at high scale. So that's the idea that we use. That's the knowledge that we use. Now, as expected, quantum gravity breaks all these two Z2s, and as a result of which, this dark matter is allowed to decay, and we know that the lifetime of the decaying dark matter is highly constrained from CMB. So this in turn can provide a constraint on the scale of quantum gravity. On the other hand, the 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 quantum gravity actually introduces a bias term in the potential, and that actually allows the domain wall to annihilate, and hence it can generate the gravitational waves. So this in turn can also constrain the scale of quantum gravity. So the other important issue that we wanted to address in this work was to explain the nanograv result, and as can be seen from the plot in the left bottom, we were able to explain the nanograv result with certain choice of parameter in our model. Now let me talk a little bit about the model itself. As I said, we had two scalars, so one can write all the Z2 conserving interactions. So one can think of the following interactions in the scalar potential, and as I said, S2 is our dark matter. That's why it does not get a vacuum expectation value. But as a result of quantum gravity, this symmetries were broken, and hence one can write explicit breaking term in the potential, which are as follows, and all of these are high dimension operators. Now, once we substitute the vacuum expectation value of S1, this is what we get. So this is the bias term that we generate with the help of quantum gravity, and this is how we destabilize the domain walls. Now, as I said, domain walls, the quantum gravity was also responsible for destabilizing the dark matter as well. I mean, it allows the dark matter to decay. So if you look at this term, the third term inside the bracket, it's actually responsible for the dark matter decay. So it's basically this term. Now what happens is that once the electroweak symmetry is broken, this S2 will mix with standard model Higgs, and this is the mixing angle that depends on the breaking electroweak symmetry breaking scale, mass of the dark matter, mass of Higgs, and the quantum gravity, scale of quantum gravity. And as a result of this mixing, the dark matter is allowed to decay and falling, and this is the decay channel of the dark matter. So dark matter can decay to all the standard model particles. Now, because of this decay, this should not destroy the CMB power spectrum, and hence CMB gives a very strong constraint on the lifetime of the dark matter, which it says that the dark matter lifetime has to be larger than 10 to the power of 25 seconds. On top of CMB, we also get some constraint from SK, which is square kilometer array radio telescopes. So it provides a good chance of detecting a decaying dark matter, and it says that the dark matter lifetime should be of the order of 10 to the power of minus 30 seconds. So with this constraint, we generated a summary plot in order to show the parameter space where we can work with. So here we plot in the wave versus quantum gravity plane. For different dark matter masses, we have different shades of purple and these regions are actually ruled out from CMB. On top of that, we also have black dashed line, which shows the sensitivity curve of SK for different dark matter masses. And then we have this white regime, which is basically the allowed parameter space. Here, the colored solid lines corresponds to the sensitivity curves of different gravitational wave detectors. This black dot actually corresponds to the benchmark point that I showed in the previous plot that can actually explain the nanograv result. Apart from that, we have these two color shaded region. One is gray and one is orange. The gray region is constrained from BBN. So this is completely disallowed. And the orange region is basically a region of parameter space where the domain wall can dominate the energy budget of the universe, and it can actually overclose the universe. So we don't want to go into that region. So the only allowed region is the white region of parameter space. Now, if we choose a different value of self-quartic coupling, we see that these constraints actually shift. So for a lower quartic coupling, as expected, we have larger allowed region of parameter space. So here, the idea of this work was to show how we can use gravitational wave from domain wall to test the scale of quantum gravity. So feel free to ask any questions if you have. Like, feel free to stop me.
Rishav, since you asked for a question,
Yeah.
so here and also on the earlier plot, I don't see any kind of theoretical uncertainties or anything like that. Do you have large theoretical uncertainties here, or do you have an estimate of them?
Theoretical
Yeah,
uncertainties in which
in,
sense?
in the prediction of the so in the prediction of the gravitational wave signal. So then there should be some error on the sensitivity curves, and there should be some
So actually,
error.
we took the best fit values.
Uh, you took the what do you mean by the best? I mean, what do you mean by
So
best fit?
if you look at this plot, so this is basically the spectrum,
Hmm.
and these are the volumes which was given by the given in the nanograph result. So you see that like for a given choice of parameter space or for a given choice of lambda. So here what we fixed was the this self-quartic coupling at 10 to the power of -3, and then the vacuum expectation value was around 10 to the power of 6 GeV. And you see, it actually fits quite well. But depending on the choice of
Right,
parameter, this can be shifted up and down.
right. So this brown line fits quite well for
Mhm.
these choices of the parameters,
Yeah,
but if you're but there should be some theoretical uncertainties, I think, in the way that you're actually predicting this from those
yeah,
parameters.
yeah.
So in reality, there should be some band around this brown curve, I think. Might be quite large, I don't know.
Yeah, that we didn't check, but yeah, we can definitely have a look at it. I mean, we can see the band, I mean, how it will look.
Okay.
Yeah. All right. So shall I
Yeah,
move
yeah.
on?
Please carry on.
Okay. Okay. Now, next thing I want to talk about is generation of gravitational waves from cosmic strings. So again, here are some of the references, some recent work and some well-studied, well-known works on this topic. So again, to start with, what are cosmic strings? So cosmic strings are basically one-dimensional topological defects. And when again, one can ask that how are they formed? So they are formed when this continuous symmetry is spontaneously broken. It's continuous symmetry like continuous symmetry like U1. So if it is spontaneously broken, one can have this one-dimensional topological defect. Now, depending on the nature of this symmetry, global or local, the nature of the strings can be determined. So if the symmetry is global, one expects a global string to come into picture. If the symmetry is local, one expects a local string to come into the picture. So this is how the cosmic string actually are formed. Now, again, cosmic string can also act as a cosmological catastrophe because its energy density also varies as a to the power of -2, and it dilutes slower than matter and radiation, but it dilutes faster than domain one. So just for the comparison purpose, I've shown this plot. So again, blue and black line corresponds to the matter and radiation energy density. The red dashed line is domain one, and the green solid line actually corresponds to the shows the variation of energy density for the cosmic string. And you see, even if it is a bit faster than domain one, it can actually dominate the energy budget of the universe at a later stage. But evolution of cosmic string is not that simple. It's much more complicated because what happens with string is that they actually intersect among themselves, they intercommute among themselves, and they form loop of different sizes. And mostly, uh, the smaller loop actually decays by radiating gravitational wave. So what is the feature of gravitational wave spectrum when it is generated from cosmic string? So now to start with, one can consider a loop of length L, and at later time, because of the radiation of or emission of gravitational wave from the cosmic string, one can write the length of this loop as follows. And this is the term comes with a negative sign, as it comes with a negative sign because it radiates gravitational waves, and hence its size is keeps on decreasing. Here G mu is actually the string tension, and gamma is at 50, and it comes from the simulation. So now let me talk a little bit about the typical feature of gravitational wave spectrum when it is observed from the cosmic string. So you see, the plot on the right, it has a very special feature. What we see is that the amplitude rises with the increase in frequency, and later on it actually flattens, it saturates. So one can ask why it saturates. So the reason is as follows. These these the saturation happens because this is the time when the loops are actually formed in the radiation dominated era, and they start emitting the gravitational wave. Now what we know is that this gravitational waves, the energy density of the gravitational wave also falls as a to the power of -4, same as radiation. So it dilutes very fast. But the formation rate of this cosmic string is also very large. So in the radiation domination era, what happens is that like these two effects actually exactly cancels each other. And that's why we see no dependence on the frequency at especially at the higher frequency regime. No dependence of the frequency on the amplitude of the gravitational wave. But at later stage, I mean, the string can completely decay in the radiation dominated era, or it can decay in the matter dominated era, and hence the spectrum actually falls as s to the power of -1 in the lower frequency regime, as can be seen from this plot. And this is the typical feature of gravitational wave spectrum from the cosmic string. Note that this actually depends on the amplitude actually depends on this string tension, as can be seen from this expression. It depends on g mu. Now the larger the g mu, the more will be the amplitude, and hence tuning this g mu factor can actually help the spectrum enter into the different sensitivity curve. And again, depending on the choice of parameter, one can test that model in different gravitational wave experiments. So again, I would like to discuss some applications of gravitational waves from cosmic string. So this was the work done by this group in 2021. I chose this just for giving an example, because this is a fairly simple example to show how gravitational wave generated from cosmic string can actually probe a very heavy dark matter. So the idea was simple. They extended the standard model with a discrete Z2 symmetry, and U1b minus L, which is actually gauged. So since it's a gauged U1b minus L, the cosmic strings are local, and because of the cosmic string vibration, it generates gravitational wave, as I discussed earlier. Now, in their model, this was the relevant Lagrangian. So what they did was they introduced three right-handed neutrinos and a scalar phi, which is responsible for breaking of U1b minus L. So once this breaking takes place, the right-handed neutrino actually becomes massive, and it also gives rise to a additional gauge boson. Now, the right-handed neutrino were also interacts with the standard model Higgs, standard model leptons. Yeah, but apart from that, they also introduced couple of other couple of other fields like a fermion psi, a scalar S, and this psi, and one of the right-handed neutrino, this call it as nu3, is actually odd under this discrete symmetry, and hence, depending on the mass hierarchy, they can be light. Now, apart from that, they had additional higher dimension operator that was responsible for psi to decay, for psi to decay slowly, and I'll tell you why this is important in their work. So if you look at the plot on the left, this shows the evolution of this dark matter. They call it as nu r. The evolution of dark matter with the expansion of the universe. So this Z is basically the dimensionless quantity, which is basically the ratio of the mass of this dark matter with the temperature. Now, as we can see, if the right-handed neutrino does not interact with psi, it can still annihilate through the gauge boson, through the Z prime gauge boson, or through the scalar phi. But the thing is that this annihilation, uh, total annihilation cross section is quite low, and hence its abundance is quite large. So that's why we see the freeze out actually takes place at a very high temperature. Now, apart from that, like once we take into account this interaction with psi, the dark matter is actually allowed to co-annihilate. Now, with the help of this co-annihilation, the dark matter, the freeze out of dark matter actually takes place at some later phase. But notice that one cannot take the take the coupling very large, because it disturbs the perturbativity. So one needs to be at the certain bound. One should follow perturbativity bound. So they chose this coupling of the order of 1.5, and still they found that this freeze out is taking place at a much early. The abundance is quite large, even if we consider this annihilation. So this suggests that the dark matter relic density will be very large. Now, in order to dilute the dark matter relic density, what they did was they introduced this slow decay of psi. And since the decay was very slow, the psi dominated the energy budget of the universe at certain stage. And as a result of this decay, it increased the entropy of the universe, and hence this leads to the dilution of the dark matter abundance at later phase, and hence it can finally satisfy the correct relic density of the universe. So this was the basic idea of this work. Now, uh, now, now this showed how we can probe this heavy dark matter using uh, gravitational wave generated from cosmic string. The idea was fairly simple. So note that here the dark matter is quite massive. It's of the order of 10 to the power 13 GeV. Now what they did was, one can write this string tension in terms of the breaking scale V phi, and one can reformulate this V phi in terms of the mass of this right-handed neutrino and the coupling, Yukawa coupling lambda r. Now, depending on the mass of right-handed neutrino and this coupling, one can have different values of string tension. So here they are fixed lambda r at 0.1, and then they varied the mass of the right-handed neutrino, and as a result of which the G mu was also varying. Now, as can be seen from the figure in right, depending on the different choices of the string tension, the spectrum actually can enter different sensitivity curves, and hence can be detected. So here the idea was to show that how cosmic string can actually probe a super heavy dark matter. I mean, how gravitational wave can be used to probe a super heavy dark matter. So this was the whole idea behind this work. So this was one example. Another example that I would like to give is based on one of our recent work. And here again, the idea was similar to what it was shown in the earlier work. So we had a standard model with U1 symmetry, which is gauged and which is responsible for cosmic string, and cosmic string for the decays to generate gravitational wave. And and this is the Lagrangian. We have again right-handed neutrinos that couples to a scalar S, which is responsible for breaking this U1 symmetry. So here, apart from this, we also had a PBH that can produce these particles. I won't be going into the detail of PBH, at least in this slides. I'll be discussing the PBH part separately in the upcoming slides. So here the idea was simple. Because of the presence of PBH, and another thing I would like to say is that we considered one of the right-handed neutrino very feebly coupled with the standard model particle spectrum. So this Yukawa interaction for this N3 is very small, very feeble. So it never thermalizes. So the thing is that what we considered was, we had a PBH, and because of the PBH evaporation, it produced different particles, including the right-handed neutrino. And we call this right-handed neutrino as a diluter. So in this scenario, what we had is, we had a multiple matter dominated era. First era was matter dominated era was because of the N3 domination, and then the second, as we'll see in the next plot, is since the universe was also dominated for some phase because of the PBH, this actually led to a second matter dominated era. So now I'll show how we can use gravitational wave from cosmic string to actually probe different or multiple matter dominated era. So this is basically a schematic of what we wanted to show. So as I said, this PBH was actually produced in a radiation dominated era, and gradually its energy budget actually dominated the universe, and the universe again entered into a matter dominated era. Now, once the PBH was evaporated, the universe entered into a radiation dominated era. But slowly, because the right-handed neutrino was also, the entry was also getting produced from the PBH evaporation, and also because of its slow decay, it started to dominate the energy budget of the universe. But once its decay was finally completed, the universe became radiation dominated again. So this actually is also shown in the plot in the right. So the red line corresponds to the energy density of radiation. The blue line corresponds to the energy budget of the black hole. The black line corresponds to the energy density of the right-handed neutrino or the light diluter. So as I said, at some point of time, the black hole actually starts dominating the energy budget of the universe, as can be seen from this plot, that the energy density of black hole is larger than the energy density of the radiation. Later on, the black hole actually evaporates and universe again becomes radiation dominated. And following which, because of the slow decay of the right-handed neutrino, universe again transformed into a matter-dominated era. And once the decay was completed, the universe finally entered into a radiation-dominated phase. Now, actually, because of the presence of multiple matter domination, this will show a deviation in the gravitational wave spectrum. Because I said, the typical feature of the gravitational wave generated from cosmic string is uh, a plateau and then a fall. Now, if there existed any other matter dominated era in the universe, this spectrum will be deviated from its original. So the thing, as you can see on the plot on right, we see different bends and falls in the spectrum of cosmic string. So to start with, if we look at the red curve, we denote different matter domination and radiation dominated era. Now, so we can start with a recent matter dominated era, which is basically the domination of N3. So this is the present epoch. Then this is the radiation dominated era, which corresponds to this time. Now, since the right-handed, the N3 also dominated the energy budget of the universe, this will actually lead to a bend in this, or a break in the spectrum. So it actually, we went from flat spectrum to a power law spectrum. That's why we see a bend. Now, once the right-handed neutrino actually evaporated, the we got this spectrum. Now, before again, as we can see from this plot, we had a region of parameter space where the universe was a radiation dominated era, was in the radiation dominated era after the evaporation of PBH, which is basically this part. Now, again, when the universe was in a matter dominated era as a result of PBH domination, we see the fall in the spectrum. So this is a typical signature that one can think of, or what we'll get if there was a multiple matter dominated era in the early universe. So this is how the spectrum of the gravitational wave will look. Now, here I showed a way to probe different multiple matter dominated era, or how gravitational waves from cosmic string can actually help us proving multiple matter dominated era if it existed in the early universe. So this was all about the gravitational wave from cosmic string. So again, if anyone has any question, feel free to ask. Otherwise, I can move on to the next slide.
Hi, Rishabh. This is Arvind.
Hi.
So,
Hi.
I have a question.
Yeah.
So, you talked about the gravitational wave from the cosmic string,
Yeah.
right? And
Yeah.
this cosmic string existed in the early universe,
Yeah.
maybe at the time of PBH formation, or maybe after that.
Yeah.
When? I
Yeah.
mean, it's
I
after
mean,
PBH
it.
evaporation you are talking about, or that it already existed with the
Huh,
PBH.
I'm saying that PBH was formed at certain stage.
Okay.
in the radiation dominated era. Cosmic string will be, we considered, I think its formation was above, before the this formation of PBH.
Oh, okay, okay. It's like anything like in the radiation dominated era, let's say,
Yeah.
simultaneously.
Yeah. I mean, you can study actually different scenarios. I mean, PBH can be formed before the formation of cosmic string, because these two things are kind of independent. Because cosmic string is getting formed because of the breaking scale, breaking of this U1 symmetry. That can actually happen before the PBH formation or after the PBH formation. So this will lead to some difference in this plot.
Okay. And what about the this? As you know that this PBH, because of PBH, the gravitational wave can be generated.
Right. Right. So,
yeah.
so the thing is that PBH evaporation can produce gravitons. It can generate gravitational wave. PBH mergers can generate gravitational wave. It can also generate scalar induced gravitational wave, that I'll be talking in the next slide. So here, for the choice of parameter space that we considered, we found that at least the gravitational wave generated from PBH was not, I mean, the amplitude was not that much, and the gravitational wave is actually dominated from the one which is generated from cosmic strings.
Okay, and one more question, that like you also, I think, told that because of PBH evaporation, the right-handed neutrino, so it's also producing because of evaporation, right?
Right.
But at the same time, as we know that the PBH evaporation also leads to some light particles, like normal neutrinos and all those things.
Yes.
And you are not considering any interaction between the normal neutrinos and with this right-handed neutrinos? I think
so. Yeah. So as I said, so this right-handed neutrino, we considered it as this particular right-handed neutrino, we considered it as a diluter. So what we did was its interaction with the standard model particle, it was very feeble. But other two right-handed neutrinos will definitely interact with standard model neutrino. It can explain neutrino masses. It can help in generating the leptogenesis. I mean, matter-antimatter asymmetry in the lepton sector. So we can do all these stuff. But the thing is that, like, from neutrino oscillation data, what do we know? We know that we know two mass square splittings, right? So actually one can use two right-handed neutrino to explain these mass square splittings. So in that sense, we consider one of the lightest neutrino to be massless. So still we can decouple one of the three right-handed neutrinos from the neutrino oscillation. So that was the fact that we used. We actually decoupled one of the right-handed neutrinos from the standard model baths. And then we considered it slow decay. And that's as a result of this feeble interaction, it was not produced from the bath. But since it was there in the universe, PBH evaporation will definitely produce this right-handed neutrino. Again, it depends on the mass, how much the right-handed neutrino will be produced. So these things actually I will be discussing in the coming slides.
Okay. Yeah. Thank you. Yeah. Okay.
No worries. Yeah. So now the next thing I would like to discuss is the generation of gravitational waves from PBH. And again, these are some references, but which one can look. So what do we know about black holes? So black holes, these PBH or primordial black holes, can be formed in the early universe because of the collapse of large inhomogeneities or collapse of some topological defects or bubble collision. So there are different ways by which these PBHs can be formed. Now, this is some basic information about the PBH. Now, the mass at the time of formation, since we considered the formation of PBH in the radiation-dominated era, the mass at the time of the formation can be expressed in the following way. Here, rho rad is the energy density of the universe at the time of formation, PBH formation. Then we have instantaneous temperature of the black hole, which actually depends on the initial mass of the black hole. Now, as I said, this PBH will actually evaporate, and as a result of its evaporation, its mass will keep on changing. And this is how the rate at which the mass of PBH changes. It also, again, depends on the initial mass of the PBH. Another important quantity or the thing is this beta, which is basically the ratio of PBH energy density with the radiation energy density. And if we want PBH to dominate the energy budget of the universe, one needs to satisfy this condition, which is beta should be larger than beta critical. And this condition also again depends on the initial mass. Now, this PBH masses are constrained, as you were saying, as Arvind was saying, that PBH can evaporate many particles. So it can also evaporate light particles. So the thing is that, like, PBH evaporation should not alter with the BBN constraint. So actually, BBN gives a constraint on the mass of upper bound on the mass of PBH, which is around 10 to the power of 8 grams. On the other hand, we get a lower bound of 0.1 gram from CMB. This is because what we consider is that the Hubble expansion rate at the time of PBH formation should not be larger than the expansion at the time of inflation. So this actually gives you a lower bound on the mass of PBH. So which is around 0.1 gram. So again, on plot on the right, I show the energy density of different component with the scale factor. As expected, the radiation energy density falls faster than the matter. And since PBH actually acts as a matter, we see that the universe becomes a matter-dominated era for some time, for some point, till some point of time. And after the evaporation of PBH, the universe again enters into a radiation-dominated era. Now, this is basically a fact sheet about PBH. I just plot the variation of different temperature, that is the temperature at the time of formation, the temperature, the instantaneous black hole temperature, the evaporation temperature of the PBH, with the initial mass of the PBH, and this is how the different temperature varies. And as expected, all of them has an inverse dependence on mass. So that's why the temperature actually decreases if the mass of the PBH, initial mass of the PBH is considered to be large. Next, in the second plot, I wanted to show the region of parameter space where the PBH can dominate. We used the condition showed in the last slide, the critical value, choosing the critical value of beta, we can get the region where it can dominate. So here the white region is actually the region of parameter space where the PBH can dominate depending on its mass. The gray region is the region excluded from gravitational wave. This bound actually comes from N effective. Since the gravitational wave behaves as a radiation, it should not it will be constrained from N effective. So that's why we get this upper bound on, that's how we get the upper bound on beta. Now in the third plot, I show the variation. Again, I show the variation of energy density of the ratio of energy density of black hole or different components with radiation. So to start with, the universe was dominated by radiation. And in that radiation dominated era, the black hole actually came into the picture. The energy density of black hole gradually started to increase with the expansion of the universe. And then at certain stage or certain epoch, the universe became matter dominated because of the PBH domination. And once the PBH evaporated, the universe again transformed into a radiation domination era. So now let me talk a little bit about particle production from PBH. So the number density of the particle produced from PBH actually depends on the mass of that particle and also the instantaneous temperature. If the mass is lesser than the instantaneous temperature at the time of formation, the number density actually depends on the mass of black hole. If the mass of the produced particle is larger than instantaneous temperature at the time of formation, it actually depends inversely proportional. It actually depends inversely with the mass of the particle produced. Now we can use this information actually to study leptogenesis or to produce a particle which is unstable and is responsible for leptogenesis, for example, right-handed neutrino, as I was saying. And this is actually a allowed parameter space where on a plot on the right, or the top right, actually shows the allowed parameter space where one can do a successful leptogenesis. So this white region is the only allowed region where one can have correct leptogenesis, or where we can explain the baryon symmetry of the universe. And one notices that the mass range of PBH is very much constrained. So the PBH is quite light. One needs a light PBH if you want to do a successful leptogenesis. On top of that, since the PBH can evaporate air, can produce any particle, it can also produce a particle which is stable and can play a role of the dark matter. And this is what the parameter space looks like for the dark matter. So in y-axis, we have the mass of the dark matter, and in the x-axis, we have the mass of the PBH. And what we see is that only the correct rally can be obtained on this black dashed line. And we find that the allowed region of parameter space is also very restrictive. It can be easily seen that only a heavy dark matter can actually be produced from PBH that can actually satisfy the correct relativity. It can also produce light dark matter, but it is completely ruled out from the Lyman alpha bound. So next thing I wanted to talk about is the gravitational wave from PBH evaporation, not from PBH evaporation, but the scalar induced gravitational wave. So actually PBH, as I said, PBH can produce gravitational wave by different mechanism. It can evaporate, produce gravitons, and that can actually generate gravitational wave. It can merge because of the PBH mergers. It can release energy and generate gravitational wave. And the other thing is because of the distribution of PBH, because of the inhomogeneity in the distribution of PBH, it actually generates the scalar induced gravitational wave. So what happens is that when the PBH is formed, because of this inhomogeneities, isocurvature perturbations are generated. And when this isocurvature perturbation actually increases, and once the PBH evaporate, this isocurvature perturbation is actually converted into a curvature perturbation, and hence it generates a gravitational wave. So there has to be a transition between matter dominated to a radiation dominated era, and that's only when one can generate the gravitational wave. So the spectrum actually looks like this. So it increases, then it reaches the peak, and because of the evaporation, the spectrum falls very rapidly. Now this peak actually corresponds to the point when PBH evaporation took place. If we consider an instantaneous evaporation of PBH, this peak corresponds to that epoch. So this is how one can generate gravitational waves because of the scalar induced gravitational wave because of the distribution of PBHs. Now, again, one can think of some of its applications. So we did this work where we wanted to test, where we wanted to do baryogenesis, and we wanted to see if we can use gravitational wave generated from PBH. The question that we had in our mind was that can the gravitational wave generated from PBH, can it test the baryogenesis, or can it be a probe to baryogenesis? So here the idea was that we introduced two scalars which carried a colored chart. So this was baryogenesis, not leptogenesis, and one fermion, which is actually required for the generation of the symmetry. You see that this psi actually couples to the standard model quarks and these fermions. It also couples to up type quarks, and it couples to the down type quarks. The decay of these two S can generate asymmetry in the visible sector. If there was no coupling to the psi, the asymmetry would have been washed out because of the flavor sum. So that's why we need another fermion to generate the asymmetry. Now, and we also need at least two generation of scalars to generate asymmetry. So what we did was we considered the mass of these two scalars to be very close, and this mass splitting we considered to be 0.1 GeV. So we kind of had a resonance baryogenesis in this scenario, and the total asymmetry was actually the sum of the asymmetries generated from these two scalars. So since the mass was we consider the mass to be degenerate, one can take the ratio ns1 by s and ns2 by s will be more or less the same, and hence we can take these two things common, and the baryon symmetry will depend on the sum of these two CP symmetries. Now here in this plot, what we show is the region of allowed parameter space where one can have a successful baryogenesis in the coupling versus the mass of scalar plane. So the blue line actually corresponds to the region of parameter space where the correct baryogenesis can be done. And these, we get two upper bounds because of the bound that comes on the mass of PBHs from CMB and BBN. The red region is completely disallowed because one cannot have a very light PBHs. Then this had an additional constraint from neutron anti-neutron oscillation. So in this white region, one can have different masses of black holes, which is actually allowed from the experiments. So again, in the left plot, we show the parameter space in MS versus the mass of scalar versus MN plane. And we found that the maximum asymmetry that we can get in this model was, the sum of the asymmetry that we can get in the model was of the order of 0.4. So it was not possible to get asymmetry which is larger than this. So this pink region is completely excluded. So these different blue lines actually corresponds to the correct baryon asymmetry of the universe. But this was all about how how one can explain the matter-antimatter asymmetry of the universe. In the right plot, I show how we used the scalar-induced gravitational waves from PBH to test our scenario or to prove our scenario. Now, depending on the different choices of scalar masses, we will get different spectrums that can be actually tested or observed in different gravitational wave experiments. So this was all about all what I wanted to discuss on how gravitational waves can be used to probe the high-scale physics of the early universe. So finally, I would like to conclude and summarize by saying that there exist some issues at high scale or cosmological puzzles at high scale, like dark matter, baryon symmetry, scale of quantum gravity, PBHs, but there are no probes or there are no concrete probes to test these scenarios. So the question that we rose was that can we use gravitational waves to probe these scenarios? Now, how can we generate these gravitational waves in the early universe? This can be generated from phase transition, topological defects, and PBHs. So in this talk, I covered two of these sources, where topological defects and PBHs. Now, as I said, these sources can also produce particles which are responsible for these cosmological puzzles. So this suggests that the gravitational waves and these cosmological puzzles might have a common origin, and hence one can use this gravitational wave to understand, test, or probe these high-scale physics in the early universe. So finally, I would like to conclude by saying that gravitational wave cosmology is one of the most promising avenues for discovering physics beyond the standard model. Thank you.
Okay, thank you very much, Rishav, for the nice talk. So we already had some questions,
Sure.
but I'm sure there are some more. So if you have a question, can you try to use the raise hand facility on Zoom, and I'll then invite you to ask a question, or if you're having problems with that, just unmute and ask. Okay, I see applause from Christian, but I don't think that's asking a question. So while people are maybe thinking of questions, let me just annoy you again about these theoretical uncertainties. Sure. I mean, I don't have really a deep knowledge of domain walls or cosmic strings and these things, but I just know from first order phase transitions that they are people who would ignore uncertainties for a long time, and now we discuss them much more, and I'm pushing people to really think about the fact that these are like really quite large uncertainties, orders of magnitude.
I mean, this gravitational wave simulation is not that easy. I mean, it will have uncertainties.
So exactly. So that's why I was asking. I think it applies to the cosmic strings, and it also probably applies to the
all the spectrums.
So this is something that I hope in future can start to be shown on these plots, and then we see.
Definitely. Yeah, it's a good thing actually to show these uncertainties.
Good. So if you're having problems raising your hand, please just unmute and speak up.
Hi, Peter. I think, can I ask a question? Because
Yes.
I think I'm thinking about it.
Yes, please do.
Yeah, Rishabh. So this is regarding the same thing. So you also discuss about this baryogenesis from the gravitational wave, PBH.
No, PBH, baryogenesis from PBH.
PBH. So what does that mean? So PBH evaporate in different particles, like all the fundamental particles and dark matter, right? Depends on the temperature and mass.
Right.
So how, I just curious to know how this happens because of this.
So as I said, I'm not able to change the slide. Yeah, so as I said, so we had these scalars that carried a colored charge, and one can show that this scalars actually is not into equilibrium at certain stage. So the thing is that since it was, I mean, we did basically non-thermal baryogenesis, then one can think of a scenario where these scalars are also in equilibrium. They were produced in the early universe because it carries a strong charge, a strong interaction, right? So one can think of a scenario where these scalars are produced in the early universe and was decaying and was generating the asymmetry. So, and on top of that, since PBH was formed at some later stage and it evaporated, it can also produce these scalars, right?
Right. Yes.
So we had two different kind. We can have two different kind of scalars. One is thermal and one is non-thermal, and both of them can generate actually asymmetries. And one can see a scenario where how these asymmetries actually evolve. So we did an earlier work where we didn't do baryogenesis, but we did leptogenesis, and we considered thermal right-handed neutrinos as well as non-thermal right-handed neutrinos, and how the asymmetry evolves when we consider these two things into the picture. So here we just, for simplicity, we just considered this S was produced from PBH evaporation, and then they decayed and generated asymmetry.
It means that they are not produced in the early universe because of.
I mean, it can be produced.
Let's say, but you are saying that even the PBH evaporation is sufficient to sufficient.
If S was not present in the early universe for some reason, I don't know what, PBH can produce this S, which can actually decay, and this decay will be fast because the duration of decay will be very less, because if the temperature of the universe is smaller than the mass of this scalar field, this S will decay very fast and it can generate asymmetry. Yeah, this was basically the whole idea.
Okay. So one more thing, like, as we know that the PBH evaporation depends on the temperature, right?
Yeah.
Temperature of the black hole, and temperature increases as mass decreases 1 by m because of evaporation. So we expect that at a later time, when evaporation is sufficiently large in the sense, then we in principle get more leptogenesis, or let's say baryogenesis, right?
The thing is that, like, as I said, it depends on the mass of the particle which PBH is producing.
Right.
So if the mass is smaller than the instantaneous black hole temperature, the number density actually depends on the black hole mass. But if the mass is larger in comparison to the black hole temperature, it is inversely proportional. The number density is inversely proportional to the mass of the particle. So in that case, like, again, if the mass is large, the number density will be smaller. If the mass is less, the number density will be larger. So that's the kind of tuning you need to do.
Yeah, that I can understand. But one thing I can little curious, like, because this kind of thing depends on also the evaporation rate, right? What I am thinking that evaporation basically increases fastly at the late time, right?
Yes.
Because temperature is increasing because of the evaporation. So I will expect this effect will be like, if I plot n chi versus a time scale, right? Then I will expect that at the time when T evaporation, T is equal to T evaporation time, it should be very high.
Yeah. Again, it depends on the mass of that particle. But let me show you a plot that I was saying. So here, as I said, you see, this is the number density of black holes, number density of right-handed neutrino, which is not number density, but energy density. I mean, this is just for the demonstration. But as you were saying, at the time of PBH evaporation, it increases very fast, and it will increase. So this is actually clear from this, from this plot.
Okay.
Yeah, I mean, and then you can tune it accordingly to get a right abundance of that particle if you want to do leptogenesis or if you want to do dark matter.
Okay. Thank you.
Yeah, no worries.
Nice talk. Yeah.
Thank you.
Okay, thank you. Let's just see if there's anyone with one quick more question. Otherwise, we can stop. I don't see anyone with the hand raised. So last chance to unmute, or we're gonna close the session. Okay. Seems not. So let's thank our speaker again. Thank Rishav for a very, very nice talk. And yeah, well, I look forward to seeing you in Southampton, and
definitely, eagerly waiting.
Maybe one day you can also come over here to China and give a talk in person.
Definitely.
Okay, so thank you very much, and see everyone later.
Yeah, thanks for having me. All right.
Bye.